So this week and next week we're going to be here, so you see quite drastic change of location. We were thinking that it would be nice to introduce ourselves so that we all know each other. So my name is Enrico Bertuzzo. I am a professor here at the University of Sao Paulo. I work in Vienna standard model. I've been interested in the past in the naturalness problem, more recently in models of dark matter and effective field theories.
My name is Csaba Csáky. I am from Cornell. I'm also one of the organizers with Enrico and Gustavo and Christoph.
He's arriving on Friday.
Yes. And so I work on BSM, all aspects. Recently we were mostly interested in monopoles with John Offray and others, and crunching solutions with others.
Hi, so I'm Silvano Fischer. I'm now a professor in the University of Bahia. I work on BSM, I guess. So recently I'm doing some classical library using a lot of dimensions. And also I do some calculations, some loop calculations in areas.
Jay Hubish. I'm from Syracuse University, also working on physics beyond the standard model. I've done a lot of work of model building in extra dimensions, studying effective theories of the dilaton, and most recently I've had a lot of interest in applications of quantum information science to particle physics problems.
I am Ricardo. I'm a professor here in FD, where I'm also the vice director, and I'm working in BSM and especially composite Higgs models and some clustering algorithms to check for phenomenology.
Hi, I'm Alexei Macedonsky. I work on BSM now as most of us here, and recently mostly on the grading of electrochemistry at high temperature. And the models of electronic biogenesis where happens at temperatures much above 100 G. And that's something that I'm going to talk about on Friday.
Hi, I'm Joseph T.B. Smith. I'm a postdoc at Cornell. I work on kind of like gauge symmetries and classifying them, model building based on those sorts of things. Recently I've been looking at generalized symmetries in a simplified framework, which is topological field theories, and trying to understand like how they form and the basic structure of them.
Yeah, I'm Max Kudorfer. I'm a postdoc at Cornell also, and I work on sort of beyond snap model topics, also crunch solutions with high performance Java and instantons and yeah, many different things. And also recently I was also interested in amplitudes and stuff like that.
I'm Gabriele Rico. I'm a postdoc in Saclay at Paris. I'm interested in applications of ADS-CFT and of effective theories in general to BSM physics, and also to gravitational waves as a form of physics, both in astrophysical context and
I'm Matthias Hostert. I'm very happy to be here because I'm Brazilian, so it's good to be back. I'm based in Perimeter, Minnesota. I work mostly on neutrinos, connections to dark matter, and BSM in general.
John Turning, I'm UC Davis, and mostly BSM.
Gary Sherman, I'm at UCRY, BSM, quantum field theory in 4 or more or less dimensions on both instantons.
I am Shivam. I work on dark matter modeling.
I'm Peter Lenz. I'm a postdoc at USP, the
favorite terminology of DSM models, which you know, sure.
And of course we have our speaker today.
Yeah.
Say a few words.
Yeah, hi, well, I'm this guy here. And I work in this place here, I'm joking. I'm Daniele, I'm a postdoc in Sapienza in Rome. I guess,
so, if you want to start.
Yes, so today I was talking about some work without no reason, to be honest. But I'm talking about this because recently I started again thinking about this kind of QCD-like theories, with which I worked with these folks here. This was based in Florence a few years ago, and also with Enrico a couple of years ago, and a student of his. So lately I've been thinking a bit more about this, and so I took the occasion to give a talk on this. So I was supposed to give a talk last week, so I was lazy enough not to remove my introductory slide on the standard model, so you'll have to hear this. Okay, just quickly, I mean, we know the standard model is a good theory up to really short distances, 10 to the minus 19 meters, and we have minor variation with respect to the standard model prediction in some observables. If I have to bet, I wouldn't bet on anything, but maybe these are the ones that we will put our hope on, and maybe in the next years we'll have a definite answer on these flavor anomalies, especially RK, which maybe might not be true, but who knows. So we all know that there are tuning problems in the standard model. Most famous is the hierarchy problem. Then there is a flavor pattern of the standard model which is unexplained, and the strong CP problem. And this might hint to physics beyond the standard model, which is surely needed for experimental observation reason. Dark matter, neutrino masses on oscillation, and the fact that we're here and there is a baryon symmetry in the universe. Okay, general relativity is the right theory of gravity, and the lambda CDM model reproduces a large amount of cosmological observation, but we still don't know what this guy here is, what that matter is. Still with some tension. So where do we stand? Okay, so when I started PhD I was here, you cannot read it was 2011. So the LHC just turned on, we all had the hope to find new physics at the TV scale as soon as the LHC was turning on. And well, this principle of naturalness has been our guidance for, many decades. Then we turned the LHC on, and what we obtained were these results from experimental direct searches. So we're in a period where ESM models are facing results which are all negative. They're not negative, we're exploring, so we don't know what we're finding. So they're results, whatever nature tells us. But still, from the point of view, if you wanted to have some new physics, maybe they're not positive, let's say. So I think we're in an era where we have to pursue two directions. So first of all, we have to realize that LHC is sensitive to TV scaling physics with order of weak coupling, or stronger, of course. Still, new physics associated with natural is not in a good shape. There are stringent bounds. Most models have pushed in corner of the parameter space, but still they're being tested. So it's really important to look for what are nowadays called like hidden signature, like particles with exotic decays, long-lived particles that can manifest themselves in some way we haven't thought about it yet. So this is an area which I'm working on actually with Enrico at the moment, also other collaborators. So there are many experiments at the LHC besides Atlas and CMS which are active or may be active, some proposal which can investigate especially long-lived particles. So this is to say that the LHC potential should be really fully exploited. It's not, this is really important. We have a machine and we have to use it. Another approach is to relax the natural criteria and focus on something else, experimental evidences. For example, the fact that we have dark matter, neutrinos, baryon asymmetry, and just don't care at all about the hierarchy problem. Okay, this is well, now not much less, but this is still a plausible scenario. And this kind of theories, QCD-like theories, which I will talk about now, offer large model building opportunities in this respect. So this is the outline of my talk. So I will introduce this framework of QCD-like theories. So one important thing of these theories is that they're important for dark matter phenomenology, which has been explored not by myself, by other people in the last years. Then I'll talk about something I've done in the last year about direct searches on this theory and how the boson is important in this kind of theories. And then some experimental tests from collider to gravitational waves. And then it's not even work in progress, just some thoughts I have, and this is why I wanted to talk about this kind of works. Okay, so these theories
have been, well, I don't think firstly, but in 2009, Killick and collaborators proposed this kind of theories as a plausible extension of the standard model, without any other reason that the fact it was plausible. Okay? So the ingredients of this kind of theory are simple. You have a new strong interaction, a dark, I will call it dark color for the rest of my talk, so it's some dark sector with a with a gauge symmetry G dark color that confines on some scale, which I will call lambda dark color. The important thing is that new fermions, which are present in this new strongly interacting sector, on their charge on this dark color group, are vectorial, both under the standard model group and the dark color group. Okay? So that's all. Nothing else. Of course, the quantum number of this guy is important. So the fact that this fermion are vectorial, well, of course, has a benefit. I mean, there is a trivial cancellation of the gauge anomaly. You can have a bare mass allowed in theory for this fermion, which are vector-like fermions. And important, the fermion condensate, when this new sector confines, so the SAIFR condensate doesn't break electroweak symmetry. So these theories are safe, we're almost safe with respect to electroweak precision test. And this is clearly the crucial difference with respect to technicolor. And there is no relation at all with the natural to the Higgs mass. The Higgs is elementary, the Higgs sector is fine-tuned, there is a Higgs potential put in theory, and that's all. So I will talk about at the end of something. So this kind of theories are used, however, in a mechanism at least proposed like 6-7 years ago by Graham and collaborators to dynamically relax the electroweak scale to the observed value through the cosmological evolution of some new fields. So this theory are used as an ingredient of this series, which okay, so and I will talk about this at the end of my talk. So how do you build this kind of theory? So I'll just guide you through the building of this. So it's all basic, but just to build it. So let's switch off the standard model interaction. So standard model is not present. And let's consider a dark color group, which could be an SUN group, an SON group, an SPN group. And I will focus on SUN group for an easier analogy with QCD. Well, also this other possibility, these other groups are possible. And let me consider a certain number of flavor of fermions in vector representation of this dark color group. Okay, so this is Lagrangian of my theory. So working in a chiral limit, so with masses smaller than this confinement scale than the dark color, this theory possesses this accidental global symmetry. Okay. Other representation for the fermion or other groups might have slightly different property, so we'll follow this. So there is a global accidental symmetry in this theory. So, of course, when the strong sector confines, there is a spontaneous symmetry breaking, and there is a residual global symmetry, which is this SUN flavor vectorials times a U1. By construction, this dynamics is QCD-like. So there is NF squared minus 1 pseudo-Goldstone boson, which I will call dark pions. Clearly, if you want to have confined, you need to have asymptotic safety, so there are some constraints on the number of color and the number of flavor. And together with this Goldstone boson, you create also higher spin resonances like dark meson, dark baryons, and so on and so forth. Then you switch on the standard model interaction. So you assume that this guy, this psi, are charged on their standard model symmetries. So when you do this flavor rearrange in something we can call, I will call a species, which the number of species is smaller than the number of flavor. Just to make an example, suppose you have 3 flavor, and their quantum number is such as they will combine 2 species, for example, a doublet of SU2 and a singlet of SU2. So this is a model I will use called L plus N, because this is the quantum number of the lepton doublet on the electroweak singlet. And this, now the model dynamics is fully specified by this fermion quantum number. This covariant derivative now acts with respect to the standard model group, and you break this SUN flavor symmetry. So what happens now? So the dark pions with standard model charge are also massive in a chiral limit. There is a mass splitting between the singlet and non-singlet dark pion. Okay, when you switch on this, when you gauge the standard model symmetry. And also this, the accidental global symmetry now gets reduced to the products of U1. Okay, so the SUN flavor accidental symmetry is broken to a product of U1 symmetries. The last ingredient, which is important ingredient for this talk, is that depending on the charges of these new fermions under the standard model group, Yukawa interaction might be allowed. Okay? So you may be able to write an interaction with the Higgs. This is an important ingredient. First of all, this interaction breaks some of this U1, which are, let's call it species number. So this product of U1 that you had before is broken to a global U1 times whatever is not present, or whatever U1 associated with what is not present in this Yukawa interaction. At the end of the day, there is at least one U1 symmetry. So dark pions made up from different species here can decay via the interaction with the Higgs boson. And importantly, when the sector confines, there is a mixing is generated between the Higgs boson and this dark pions. Okay? So when this guy confines, there is a mixing generated between the Higgs boson and these pions. So at the end of the day, the Higgs turns out to be somewhat a partially composite state. So there is a linear mixing between the Higgs and this dark pions. So why this is appealing? This is appealing because in the context of dark matter, this has been studied in the last year. So dark matter stability is normally achieved by imposing an ad hoc symmetry in the theory. But the standard model is teaching us that this is not necessary, of course. I mean, the proton is stable because there is an accidental baryon number conservation. The electron is stable because, well, charge conservation or electron number conservation. Okay? So this theory is appealing because there is an accidental U1 symmetry. There might be accidental symmetry that guarantees the stability of some composite state. Okay? For example, the conservation of this U1 factor, the species number, forbid the decay of dark pion made of different species. If you take as an example the system of QCD and QED, so no electrolytic group, just QED, this is the same as saying that the pion in the system will be stable because the number of species up and down is conserved. Okay? A more, let's say, protected symmetry, a symmetry that is more stable in the parameter space of the model, is the dark pion number, so which is the sum of the species number. This is conserved, and the lightest dark pion is stable. So this kind of theories predicts many accidental stable states. Okay? So this is just an analogy with the QED-QCD system, just to wrap up what's the framework. So in the QCD-QED system, we have vector-light interaction between the quarks with respect to the U1 electromagnetic and the SU3 color, and here you have vector-light interaction between the standard of the dark quarks with respect to the standard model group and this dark confinement group. So here is the analogy between the chiral condensate that doesn't break electromagnetism in the system, and here it doesn't break G standard model. The neutral charge pion mass splitting due to the gauge of U1 electromagnetic, which is the same in the dark sector. Stability of the proton, stability of the lightest dark pion. As I said, species number conserved, some pions are stable, and importantly, some pions can decay the anomaly, depending, of course, on the quantum numbers of the constituent fermions. So all this has been worked out in this paper by ICTP and collaborators. So what they focus on some kind of quantum number assignment in ultraviolet theory for the new fermions, and they studied whether there are theories that can predict good dark matter candidates. Where with good I mean dark matter candidates which don't have electric charge and don't have hypercharge. Okay, so they found some what are called golden class models. So stable states which are dark matter candidates. They found also other models where you need to break some accidental symmetry because, for example, you have a charged particle which is stable, so this is not viable. For example, the simplest model is a model with a single species, so a triplet of SU2 with no hypercharge and no color, and with 3 dark color. So dark pions and dark pions are in 8 of SU3 and flavor. This decomposes as a 3 and 5 under the standard model group. Both the triplet, or the lightest baryon in a triplet and the lightest pion in a triplet are stable. The baryon again because of dark baryon number, the pion actually because of different symmetry which is called G parity, which is this combination of charge conjugation and isospin. Anyway, there are stable states which can be viable dark matter candidates. They categorize all this, I don't want to go all this table. you can find in this paper, they categorize all the possible models which give a viable dark matter candidate under the assumption that the quarks belong to fragment of SU5 irreducible representation. So they also discuss the thermal history in this kind of scenario. So there are two different, well, there are many different possibilities, but two, let's say, two opposite regimes are the following. They depend on the hierarchy between the dark color confinement scale and the mass of the detecting fermion. So suppose the mass of the detecting fermion is lower than the dark color confinement scale. What happens when you evolve in the early universe? You have dark color confinement, then you have the freeze out of dark gluons, and at the end, what they work out is that the thermal relics is achieved for dark baryons for masses around 100 TeV. So there is a geometrical cross-section, annihilation cross-section. So if you crunch the numbers, you just get this 100 TeV. The opposite regime is the regime in when dark quarks are heavier than the dark color confinement scale. This has been worked out in this paper by Mitridate and collaborators. So there is first a dark quark freeze out when the temperature goes below 1/20th of the dark quark's mass. There is a confinement of dark quarks, and then there might be a freeze out of dark gluons later on. So the dynamics are very complicated, but at the end of the day, dark matter in this scenario can be lighter. Okay. Also, dark matter phenomenology is really important, it's really interesting. Dark nucleosynthesis has been studied by the Radian collaborators, so dark matter could be made up of dark nuclei. Okay, there could be a dark nucleosynthesis process with the interesting phenomenology. And interesting, there are consequences for indirect detection. So bound state formation can lead to multi-line signature, which are relevant for indirect detection. You can have multi-monochromatic lines from the bound state formation of some two dark nuclei. Okay, so there is a rich phenomenology here. So what we wanted to do? So what we wanted to ask is what are the direct tests of these theories? So can these theories be tested at collider and low energy experiment, and how they can be tested? So what's the coverage, and what can be done at the LHC for this kind of theories? We did this in this paper with the Curtis and Tesi a few years ago. So my working hypothesis would be to focus on the QCD-like regime, so in a regime in a chiral limit, let's say, so mass is way below the confinement scale. Consider color-neutral fermions, and consider a model where there is a Yukawa interaction with the Higgs, because this allows for interesting phenomenology. The spectrum of the theory, which I will write in the next slide, is the following. You have the interesting player, or the pseudo-Nambu-Wilson boson, the lighter states in the theory. Higher spin resonance like dark rose could be important, while the lightest baryon might be too heavy to be accessible at the light. So what quantum number can I choose? Okay, this is a choice. We chose to focus again on a fragment of SU5 irreducible representation. So here there is a big distinction to be made. You can choose quarks charged on the SU3 color. This gives rise in general to color technivions. These are really easy to reduce, but this has been largely studied at the famous diphoton time, because that was the prototype of the diphoton resonance, so something produced via gluon-gluon fusion and became the anomaly in the birth photon. So we were focusing on the more challenging scenario of color singlet quarks, which give rise to pions just charged on their electroweak symmetry. And we'll focus on these two models. So this L+N model, which allows for a Yukawa interaction with the Higgs boson, and a model with just a triplet, the one of the simplest dark matter model, which I mentioned before. Both of these has 3 flavors. So the L is 2 flavors plus a singlet, and this is a triplet, so there are 3 flavors. So this allows for an easy analogy with QCD. Okay, the model is simple. So the ultraviolet Lagrangian. The ultraviolet Lagrangian is the following. The mass term for the spectral-like fermions and the Yukawa interaction with the Higgs boson. And in the confined phase, the dynamics is described by a chiral Lagrangian. So you have a kinetic term for the pions, so you have a mass term, and then you have schematically interaction with the the electron-weak gauge boson. Okay? So this is my mass matrix, and you see there is the interaction with the Higgs boson. So the dynamics is QCD like. You generate an octet dark pions, and the dark pions is the following. So you get from the LL bilinear you get a singlet and a triplet, and from the LN bilinear you get a doublet. And this doublet has a quantum number of the Higgs boson. So you generate a scalar which has a quantum number of the Higgs. So in the confined phase, as was anticipated before, there will be two Higgs-like states, and there will be a mixing between the Higgs boson and this composite part. So there are two important terms when you expand the Caylor-Lagrangian. First of all, there is, as I was mentioning, there is a mixing generated between the Higgs boson and this composite gown. So there is an elementary composite mixing described as this parameter epsilon combination of some UV parameter. And then there are other interactions between the Higgs boson and more than one dark pi. Also, depending on the quantum number of these dark pions which are made of same species can decay in the anomaly in electron-rich gauge boson, so there are anomaly coefficient for the decay of this dark pions, and this will turn out to be one of the most important properties of this theory. So these are my collider targets, so pions with the interplay of the spin-1 resonance like dark rhodes. But this guy will be, for my purposes, inaccessible at colliders. Too heavy. So what are the tests? What are the bounds of this kind of theories? So let's start with precision constraints. So the standard model and the strong sector, this new confining sector, are coupled through Yukawa interaction and the gauge coupling. So effects on precision physics will be screened by at least 2 powers of Yukawa over G or standard model coupling over strong G. Let's start with the Higgs. So there are 2 effects on Higgs physics. The first effect is that there is a presence of the second doublet, second Higgs doublet. Only the first Higgs doublet that has Yukawa interaction with the standard model fields. So this is basically a type 1 to Higgs doublet model. So you get the same structure, a type 1 to Higgs doublet model, and this are the rescaling coupling of the Higgs boson with respect to the standard model value. Then the Caylor-Lagrangian predicts on this higher dimension interaction, so that this nonlinearity with the strong sector gives rise to this kind of operator. So this operator, as we know, universally shifts all the Higgs coupling. So you get a rescaling of the Higgs coupling proportional to epsilon to the 4th of the mixing of the composite elementary Higgs to the 4th. So the leading effect is the one of the type 1 to Higgs doublet model structure, which goes, this is deviation, so it goes as epsilon squared. So these are the 2 effects in Higgs physics. Electro-precision observables. There is a correction to the T parameter, so the Caylor-Lagrangian gives rise to this kind of operator. So when you go in the mass basis with the insertion of the elementary composite mixing, you end up with an operator which is a T parameter operator, which scales as epsilon to the 4th. There is a contribution suppressed by epsilon squared to the S parameter, so the mixing between the W3 and the Y, and there are contributions to the W operator, so the full Fleckner operator with the standard model fields. Overall, this theory are not constrained, so let's forget about this 3D active inverse luminosity line. So the main constraint is still given by the SNT parameter, but the bound on the mixing is not that large. I mean, this is, remember, it's a mix between the elementary and composite states, which could be order of 0.1 or 0.2. There is a left bound on the mass of the resonance, and the future measurement of the charged current transit mass spectrum in what concerns the W parameter will be able to cover more this parameter space. But still, this theory is pretty safe from the point of view of the electron-weak physics by construction. Flavor physics do not impose any relevant constraint, so the only source of flavor variation are the Yukawa, the standard model Yukawa. So minimal flavor variation is automatically realized. and the effects on flavor physics are further suppressed by elementary composite mixing and decay mass. So the most constraining, the not constraining effect of this delta F equal to 1 process, which do not impose any relevant constraint on the theory. Finally, for complex phases, there are irreducible sorts of CP relation. These are encoded in imaginary part of this coefficient, or, well, depends on how you work on the imaginary part of this mass parameter. The electron EDM imposes the stronger constraints. So for complex phases, there are actually tight constraints in this kind of theory, okay, which arise from this this diagram. So what about collider physics? So collider physics can be studied with the phenomenological Lagrangian to study the lighter state, which are the eta singlet, the k doublet, the pi triplet, and the spin 1 rows. So I will use the simplified Lagrangian. So the simplified Lagrangian has a kinetic term for the pion and the kaon, which describe the pion and the kaon per production due to the exchange in S channel of W Z boson. So there is interaction between this new spin 1 resonance, like a dark row with the pion and kaons, and the interaction with the standard model fermion carrier. Okay. Everything is controlled by the absolute value and relative ratio of the 2 Yukawa of the theory. So 1 Yukawa, remember, you controls the mixing between the elementary Higgs and the composite kaon, this Y minus. And then there is another Yukawa which controls the interaction of the Higgs with the additional pseudo-number Wilson boson. So when this coefficient is turned off, the Higgs, there is no mixing between the Higgs and the kaon. So the Higgs is totally elementary and this kaon are completely decoupled. So if this mixing is turned on, then the value of the kaon then will generate also the mixing with the Higgs and the singlet and the Higgs and the triplet. So in this case, all the pseudo-number Goldstone boson will mix. This means that you will be able to produce all the pseudo-number Goldstone boson through the rescaling interaction with which you produce the Higgs. So we'll have an interaction proportional to the one of the Higgs boson rescaled by some mixing parameter. Okay? So there are two different regimes. So let's start with the singlet. So the singlet, in a regime where this guy doesn't mix with the Higgs boson, this guy cannot be produced. It's an electric singlet, so you won't produce it. If you mix it with the Higgs boson, we'll acquire a copy with the gluons. This guy will either decay to BB bar as the Higgs, or in 2 photon through an anomaly term. So in the first case, this first case is relevant where the mixing is not important, because if the mixing is important, the main decay channel will be a BB bar. If the mixing is not important, the main decay channel will be the anomaly, but still this guy won't be produced. The only production will be via vector boson fusion through the exchange of gate boson, so it will be subnominal. In the other case, you can produce this guy via gluon fusion, but this is hopeless to look for it. It will be buried under QCD background. So this guy will not be important for phenomenology. The doublet is more interesting. So in a region where this guy mixes with the Higgs, you have a heavy Higgs production and decay phenomenology. So it's a heavy Higgs with the standard model Higgs decay pattern, rescale. However, if there is an interaction with the other pions, we can have what we focus on were the most interesting signature in the scenario. And one interesting signature is the one where this kaon decays to Higgs and the singlet, which is given by this Lagrangian term. Why this is interesting? Because the singlet will decay in 2 photons, in general, the anomaly. And this is kind of a per production Higgs boson searches in a bottom 2 photon final state. But what you gain is that the Higgs boson decaying 2 photons in the standard model is 2 per mil, while this decay rate can be order 1, 10% or so. So if you actually use actual data, you can set actually a bound, a constraint on this theory. You can test this theory, and this theory could be tested down to mixing of order 10 to the minus 2 with 13 TeV data. Remember that the electric precision test limit this value of epsilon to be 0.1. So direct searches could enforce really tight constraint. You can test this theory down to really small mixing. This is just because of this ratio branch duration to photon and the fact that the Higgs to photon is really small in the standard model. Okay. The most important signature, I think, is the one of this guy, the triplet. So again, if this guy mixes with the Higgs, what happens at the end is like a heavy Higgs as a standard heavy Higgs phenomenology. But in the limit where this guy doesn't mix with the Higgs, so you can still produce this guy via his kinetic term, so exchange of W, and you will decay the anomaly in multi-boson final state. This multi-boson final state are pretty interesting. So if you work out the branch ratio of this dark pions in standard model final state, you see that the dominant decay final state always involves photon, and the dominant production cross-section is the one for giving a charged pion and a neutral dark pion. So at the end of the day, the main signature you get here is a 3 photon and a W final state. This is pretty clean. You have 3 hard photon. Cross-section is quite large, it's order phantom, and then more important is, depending on the mass of this spin-1 resonance that can mediate this interaction, it can be resonant mass. So we ask ourselves, what are the limits? Is the LHC sensitive to this kind of theory? The answer is not really. So there are multi-photon final state at LHC, but so there was this old paper of Atlas which has now been updated, but it doesn't change too much. So there are multi-photon final state, but mainly they target this kind of signature where this A is a really light axion-like particle, let's say, a really light scalar. Or some standard model exotic process like this ZK. The important fact is that what they ask for, what they require are really low PT photons, and these are not optimized for this kind of signature, where you expect this photon to have a PT of the order of the half of the biomass. So what you can do? So what we did, we did the simulation, we looked at the signal, we looked at the relevant background, which are irreducible 3 photon background and fake background with 2 photon and the jet is identified by photon. So clearly this is the leading photon PT, which is harder than the leading photon PT for the 2 kind of background. This is the third photon PT. Again, the third photon PT is harder for the signal than for the background. And using current data, the data of the analysis I showed before, this in a parameter space where on the x-axis I have the dark pion mass and on the y-axis I have the dark raw mass, this is the limit you can obtain with current data. This line might slightly be moved by update search, but this is what you get. As you see, the bound is order of 200 GB. With the same data set, ATV data, 20 inverse femtobard, by asking just increasing a bit the cut on the photon PT, asking for hard photon, you can get these 2 lines. So you can actually increase by more a factor of 2 the region of the mass of the dark pion. Interesting, this region, which is excluded by the search, is complementary to the region where you directly look for this dark rows, which are like the Z prime stuff, they get into lepton. The reason why these 2 complement itself is because when above the threshold for the decay of the row into pions, the main decay of the row will actually be into pions, so you actually are in this region and you're constrained by our analysis. But when this decay channel is closed, you're in a region where dilepton search are efficient. So you actually have a nice complementarity with this proposed analysis and the existing one for direct search or spin response. Okay. Of course, you can do way better at 30 TeV. And so this is an analysis with which we're working on with CMS people in Rome.
Sorry, do you expect to relax this cut on the photon, as you were mentioning, in the new analysis or not?
So these cuts are being chosen, what we did was something similar, it was something really easy. What we did, we moved the cut on the leading photon here to see where the lines were in the optimal reach.
So in the new analysis in which you are working with the experimentalist, do you know?
This is something where, it's more up to them than to us. Okay? This is a poor theory analysis. Okay. Finally, another interesting model is this model with just a triplet. This is interesting because there is no mixing in the Higgs, so it has a really simple phenomenology. So you get a bunch of dark pions with also exotic electric charge, W charged. You can have multi-boson final state also in the states. Multi-boson final state with 4 Ws are really interesting because you can get same-side multi-lepton, and we estimate a bound of around 400 GeV. Again, in the case of 3 photon and W, you get a similar situation as for the pion with a higher cross section. So, from the collider point of view, what I wanted to say is finished. In a sense, just as a sketch of the result, if you work in a plane where in one axis you put the mixing parameter and in the other axis you put the other parameter controlling the interaction between the dark pions, you actually can cover this region quite efficiently. There are electrolysis tests at higher mixing. At smaller mixing, you have either this final state with multi-boson in a region where the mixing between the pions is not important, while if the mixing between the pions is important, you can have this kind of double Higgs production like signal. At high mixing, all the pseudo-Nambu-Goldstone boson will behave like heavy Higgs, so you have like ZZ, WW, top final state. Okay, so this is what you can do. So then I got just now I will flip topic. So why I was interested also in this kind of theory? This kind of theory are interesting because they were used also in theories that try to relax the electroweak scale to the absurd value via the cosmological evolution of a new scalar. So this is a relaxation mechanism which was put forward by Graham collaborators in this 2015 paper. So just quickly, how does mechanism work? So the electroweak depth in this kind of theory is fixed by the evolution in the early universe of the light pseudo-Nambu-Goldstone boson phi. So the potential of the theory is the following. So you have a mass term for the Higgs which depend on has a field dependent value phi. There is a slower order potential, and then there is this important ingredient which is a back reaction potential. So at the early times, so the initial conditions are such that the field phi is at 0 value, electroweak symmetry is unbroken, and this phi is slow roll due to this slower potential, and is slow roll because of upward friction. All this mechanism happens during inflation. So when the Higgs mass parameter becomes negative, when phi is equal to lambda over epsilon, there is electroweak symmetry breaking, this guy becomes negative. The trick is that you turn on the back reaction potential after electroweak symmetry breaking with an amplitude that grows with the Higgs web. So this phi gets trapped in this back reaction potential, and the evolution of the Higgs is frozen, and you end up with the right bed. So what's this back reaction? In the original paper, this back reaction was supposed, apart from the pure QCD case that doesn't work, was supposed to be generated by the confinement of a strongly interacting set. So if you have a topological term, so this H is not the Higgs, is a dual, the field strength and is dual. If you have a topological term, after confinement, just by working the QCD vacuum energy, you get an oscillating potential with phi. And if this fermions charge under this new group have a mass term which depends on has an interaction with the Higgs, you get an amplitude growing the Higgs wave. For example, in the L-cosine model, you get the back reaction potential which is proportional with some mass dependent coefficient to the Higgs wave. So with Enrico, we ask the following question. So this process all happens during inflation. What if, when you reheat after inflation, you reheat above the confinement scale of this sector that gives the back reaction? So you have inflation, here the relaxing occurs, you fix the electroweak web, then you reheat above the confinement scale, so you get the confinement, the universe starts to cool again, and at some point you end up again at the confinement temperature. If the strong sector satisfies the precisely Ricci condition, so if you have at least 3 dark fermions and 3 dark color, the phase transition can be first order, and you can actually generate gravitational wave background will be generated. So we ask ourselves whether this could be observable at present and future experiment. So there is a lot of details which I will not discuss about it. So I will refer to the paper for the details. But there is an important difference between the regimes where there is a different hierarchy between the reheating temperature the electric phase transition temperature at the confinement temperature of the dark gauge group. So this gives different evolution pattern for the evolution of the phi field. So what you end up is that potentially gravitational wave signal, potential observable gravitational wave signal can be generated. So this is a strong dynamic, so we model this dynamic with the linear sigma model, so there is all the uncertainty of the case. Still, we can be in the ballpark of a signal that can be observed at future experiments like beyond the SIGO. There is a similar paper by June and collaborator of 2019 where we worked out a similar signature in composite axion model. So this is something that might be promising for the future. These are two benchmarks that we identified with some interesting phenomenology. So, okay, I guess we're going to just flash some final thoughts I have, which are it's not work in progress, just thought. So, what I'm thinking at the moment is that if I can possibly relate this dark QCD-like theory with some other open question. One is electric genesis. So these theories feature additional CP valency phases. So I was asking myself if you can have an out of the equilibrium process to satisfy the out of the equilibrium Saccharin condition. So, okay, if I expand the chiral Lagrangian, I guess this term mixing between the Higgs and the Scown, and then I get extra term in a nonlinear expansion. So if I take the second term of this Lagrangian and go in a mass basis, I end up with a Higgs-dependent mass term for the siglet theta. So if the siglet is light, as we know, this can induce a cubic term in a finite temperature potential for the Higgs. Okay, so this cubic term is what we need for a strong first-order phase transition. Okay. In order to be strong, you need to have that the ratio of the Higgs wave over the critical temperature, over the critical temperature to be slightly bigger than 1. So you work out the expression, and you get something similar. The problem is that this epsilon parameter is related to the electron weakly parameter by this relation. So there is the T parameter is related to the mixing. So at the end of the day, you get that this ratio, well, this ratio here of the Higgs wave over the critical temperature is expressed by a function of some power of the T parameter. But the T parameter is bounded to be something less than 10 to the minus 3. So this forbids a strong first-order phase transition. The problem is that, of course, the coefficient of the mixing between the Higgs and the Cown is the same coefficient that ends up in a potential while the quadratic, the Higgs-dependent mass term for the siglet. So this minimum model doesn't work. So one has to explore some different avenues, which I'm thinking at the moment. The last thing I want to say is.
So what about the confinement and chiral symmetry?
Exactly. It's something we're thinking this day with Enrico. If you can actually use that.
Original idea with QCD.
Yes, exactly. You can use that as a strong first-order phase transition. Actually, there is a paper by who was the paper? Team Tate, where they do dark QCD biogeometries. What they do is that they put the QCD phase transition above the electroweak scale, and then at the end of the, you know the paper, no? At the end of the, okay, anyway, they put the QCD phase transition above the electroweak scale, and then you can have a strong first-order phase transition there, and then they cook the models such as at the end of the day the QCD confinement scale go back to the 200 MeV. So this is something that can be known also here. Yes, this is exactly what we're thinking. Last thought, still again thought, is that if you can have some relation with the neutrino mass. So this was put forward by Nima in '98. In actually slightly different content, because Nima was talking about chiral theories with the massless dark baryons. So in SUN dark color theories, if n dark color is odd, the baryon is a fermion. So if you have a dark baryon which is siglet or the standard model group, this can behave as a random neutrino. Okay? For example, if you take an SU3 dark group, a dark baryon, for dimensional reason, can be parameterized in the following way. So if you think about an effective theory that in infrared gave rise to the standard interaction, this effective interaction, once you have confinement, you generate a Dirac mass term for this random neutrino and eventually a Majorana mass term. You can work out some UV completion. For example, an example of UV completion of this theory is this paper by Davud Yazal in 2017. So you need extra scalar, extra matter in the UV. We can do this. The problem is simple. The problem is one, you get an extra term, but this extra term carries a baryon number equal to 1. So this dark baryon has baryon number equal to 1. So if you want to generate this operator, this implies that the U1 dark baryon symmetry must be broken. But the symmetry is linked to the stability of the dark matter candidate as the lightest stable baryon. So you jeopardize the stability of dark matter. You can play different games. Either you can reconcile a cosmological stable dark matter and neutrino mass, so have a long-lived dark matter and not stable but sufficiently long-lived. Or maybe dark matter could be a dark baryon stabilized by another symmetry, like for example G parity. Or you can generate neutrino mass through another seesaw mechanism, like a type 2. This mechanism is mediated by mu scalar, so it doesn't carry baryon number, so eventually dark matter might be stable, or something else which might be done. So there is nothing here more concrete, but this is a really nice playground to unify scenario of composite dark matter and neutrinos. So I think we're all hungry, so I'll flash my conclusion. So I'm interested in QCD light theories because I've been working on this from the collider point of view a few years ago. I worked from some astrophysical consequence a few years ago, and now I'm trying to see whether there are many more implications for neutrino masses, baryogenesis, and what are the direct tests we can have on this kind of theories. So thank you for the listening.
More questions for Daniele?
Hi, so with this collider, can you put some significant bounds on the QCD file in the relaxant parameter space? Like did you try to map?
So we did try to map, but what we did was the following. So we asked ourselves if this second relaxation phase, when you, after inflation, if you reconfine after the confinement, above the confinement temperature, you ended up again evolving a bit the relaxing field. So what we ask is whether, if the correct valve was fixed during inflation, whether this second relaxation phase spoiled the solution of the hierarchy problem. So whether you roll too much with respect to the originally selected valve. So there are regions, I didn't put the plot.
Okay, sorry, although I also wanted to ask this one, but okay, so you could use some dark photon to stop.
For example.
To
friction, you mean?
Yeah.
Yeah, sure.
I was asking about this just first, searches for those, composite states. Does that put in bounds on the
We didn't need that. The only thing you know is that, this, this is obvious. This guy here, you need an interaction with it, so you need something to be electrically charged. But this guy, there are direct search on this, so but we didn't relate the bound that we brought with the vector we did.
Maybe I can just add one comment. So we studied the collider bounds a few years ago, this time on this L+N, but at the end it's complementary to the relaxation mechanism because the parameters that enter them are exactly the same. So you always have room to actually implement the relaxation model despite the bounds that appear on the states.
So what's going on with the dark, strong CP phase?
Okay,
You
yes.
said just set it to 0, or
We did reset it to 0 there, but there is a principle dark CP phase, yes, of course. Yeah, totally, yes.
Related to those collider searches, as far as I understood that, like all the searches you were looking at were fully visible, right?
Fully visible.
But is there also the possibility to play with the parameter?
Yeah, sure.
Semi-visible.
Yeah, of course, a stable state will be either invisible or if it has charge, will be like a heavy stable charge particle that would be attracting a detector. Okay, these are targeting constraints. While if they're stable, there is dark matter phenomenology, like if you want. Yes. Yeah, there are more details in the paper. Yeah.
Curious about this dark matter. How is the direct detection done on this dark matter?
Direct detection bound. This I should remember, but I don't remember. I don't remember, to be honest. I have to check. Sorry. We'll come back to you after lunch. Sorry.
More questions for Daniele?
Dark matter is just some dark ion, like a dark ion.
Or dark baryon. I mean, the most promising, it wasn't on my work. This guy identified as the most promising dark baryons.
So these particles exist at some high energy scale. Right?
Yeah, but below the confinement scale.
We
Yes.
can like make a model where just a scalar and or fermion we can introduce as a dark fermion and paradox symmetry will be introduced to make it stable. Then could we like do some sort of mapping or correlate with your model and the new model where we just introducing dark ad-hoc by ad-hoc means symmetry, dark scalar and or maybe dark fermion that working as a dark matter. So like the pions and fermions are composite particles in your model. But there
No, the fermions are elementary. The fermions are the elementary UV degrees of freedom.
but that exists at very high energy scales, right? So I mean at low energy these are just like some fundamental particles could be.
It's like QCT, right? I mean, above you have your elementary degrees of... Maybe I didn't get the question, sorry, but... so, above the confinement scale you have your elementary degrees of freedom, then you confine, you get pions, baryons, meson, and a whole bunch of stuff, right?
Yes, so in your case it is dark SU and the two, right? So that exists at some high energy scale. So compositeness happen like lower.
Yeah, sure.
That energy scale itself is higher than this standard model.
Yeah. These guys are... So, okay, if you think about the raw mass is something like the F times G, you get something like TB scale for the confinement scale.
So what I'm saying, like the compositeness of these particles cannot be seen at low energy scale. So this is just like some scalar being fundamental scalar or fundamental fermion which is acting like that.
I mean, below the scale you're seen as elementary.
Yeah, so we can we see some correlation between, like, let's say some scalar extension of standard model there, and we have that scalar new scalar is a dark matter. Can we do some sort of checking?
Okay, yeah.
I mean, how it is this new scalar dark scalar in your model is different from the model I created where just
No, I mean, because you inherit all this bunch of interaction. So you inherit all this bunch of interaction because of the chiral Lagrange, right? So, no, where's it gone? Yes, here. Okay, so I mean, it's a different framework, so you inherit a different kind of interaction
there are more interaction involved.
Sorry?
More interaction involved that makes it different.
I mean, all the interactions suppress higher dimensional interaction, like suppressed by one. For example, I mean, even this interaction you get, right? This is a dimension 6 interaction, so you get it because this is an effective theory and you work with a chiral like Lagrange. Okay, so if you write an elementary theory, okay, you can write this or higher dimensional operator, but
Just one more night.
yeah.
So we have this dark fermion, like dark proton kind of thing. Do they also form bigger structure?
Okay, so bigger structure, I don't know, but for sure these guys have studied the possibility of dark nucleosynthesis. I mean, starting to working on dark nucleosynthesis. If they can build a higher structure, I don't know this. I don't know if this question has been asked. Maybe yes, I don't know.
Because gravity or because these are some particles having mass with gravity.
Yeah, sure. No, I don't know this. I have no idea.
Very good then. So I think we reached lunch time.
Yeah.
So let's thank Daniele again. And tomorrow, Joseph.
Can you announce when the coffee breaks are for the school?
Do you remember the time?
I think it's 10:45 in the morning, and there's one in the afternoon.
Yes.
Because I think we are invited for those.
whatever, I mean, if you need to have asymptotic fluid, so work with SUV. That's as far as your, I mean, asymptotic SAIFR have.
There's different
Okay guys, so today at 4:45 there's going to be a coffee break of the school and we can participate. It's going to be on the 4th floor.
Change the physics.
You just go up the stairs on the side of the main auditorium, you turn right and you can find
It would be a higher dimension.
Tomorrow at 10.